Hello, everyone. I'm Gabriel Martinez, and welcome back to my podcast where I interview professors. Today, I am here with
Altmannshofer. I'm a professor here at UC Santa Cruz, associate professor since 8 years now.
Ooh, that's actually great. I didn't know that. Is it okay if I call you professor, or do you prefer doctor?
No, professor is fine, whatever you prefer.
Well, professor, before we get started, I'll let you more introduce yourself, like your field of study, and how would you actually describe particle physics?
Okay, my field of study is particle physics, theoretical particle physics to be more specific. What we do in particle physics in general is we try to describe what are the basic constituents of matter, the basic constituent of everything that we see around us, and how those fundamental particles interact with each other. What are their properties? How do they behave? How do they talk to each other in some sense? And since quite a long time now, we have a very, very successful description of what's going on with those fundamental particles. That's known as the standard model of particle physics. It's a framework which has been tested over many decades now with very, very high precision, and it works remarkably well. But we have many good reasons to believe that there's more out there that's not described by the standard model of particle physics. So a lot of research in particle physics is about finding that physics that goes beyond the standard model, so-called new physics, something else that could be out there, new particles, new interactions. There are good motivations to think that there is this stuff out there, and we try to figure out how to find it.
Yeah, I know that. I did a little bit of research. I don't know, is dark matter part of particle physics?
Yes, absolutely. So dark matter is sort of one of the famous examples of why we think there's more than the standard model. We have a lot of evidence, overwhelming evidence from astrophysical observations and cosmology that there is this additional type of matter in the universe, but it doesn't fit into the standard model. None of the particles in the standard model can be dark matter, but it's very plausible that this dark matter is some other particle. So a very straightforward way of extending the standard model would be to add in a dark matter candidate that can play the role of dark matter, and that can explain, for example, the rotation curves of galaxies, or the way that galaxies move in galaxy clusters, or the cosmic microwave background, all these hints we have about dark matter.
Yeah, dark matter is interesting. I actually, I'm in a class called, it's Astro 9, and it's where you get placed in a research group. I'm part of a research group. We're working on globular clusters.
Okay.
And one of the main things, like one of our end goals, is to kind of help estimate like dark halo masses of their host galaxy.
Yes.
Do you know anything about that actually?
Very little, sort of in the details, but yeah, I mean, all galaxies, as far as we know, are sort of sitting in a halo of dark matter, and there's much more dark matter out there than the actual visible matter that we see in the galaxies. All the stars that we see in galaxies are only a small fraction of the actual mass that is sitting there. So the picture is that the actual visible mass is sitting in this halo of dark matter.
Oh, that's interesting. That actually helps me kind of figure out what our end goal is, because we've been trying to figure out what are like our steps to get to the end goal, and that actually helps out a lot. So I'll move on to, because I want to focus on the life as a particle physicist.
Yeah.
Because that's the reason why I'm doing this whole podcast, is to help students figure out what, if they're going into physics and as a major, I want this to help them kind of figure out which field they want to get into in physics.
Yes.
And this is my whole particle physics podcast right now. But why did you choose to be a particle physicist?
Well, I think I was always sort of interested in the topic in general. So I guess when I was a high school student, I was reading sort of popular science books by Feynman and Hawking, and they were talking about these elementary particles, electrons and muons and quarks and all those things. And it sounded extremely fascinating, and I wanted to learn more. And I'm still doing that in some sense, right? I still try to understand what's going on with those elementary particles, how do they behave, and now I get to do research on them and really try to understand in detail how to describe them. Reading those popular science books, you always get a very nice story, but you don't really understand what's happening in detail, of course, because these books say they don't contain any of the math background or anything like that. You can't do actual calculations or things like that, but they give you a sort of first exposure, and that sort of sparked my curiosity, and I just wanted to learn more and more about those things.
Yeah, because that's kind of the same way for me because when I'm an astrophysics major. That is kind of the same way. I always wanted to. My main thing at first was astronomy. I just wanted to be an astronomer. I had that goal ever since I think towards the beginning of middle school, and it's just always been a hard set thing for me. Do you think what was your mindset coming into particle physics?
Well, mindset. I said it's sort of mainly curiosity driven, right? I mean, you have just this this idea that you would like to understand how particle physics works. How do those particles behave? How do they interact? How can we mathematically describe that? What are the basic principles that everything else is based on? And yeah, it's really curiosity driven, trying to understand how does nature work at its fundamental level, and then you just try to learn as much as you can, all the various aspects that are required to actually make progress and understand as much as possible.
Yeah, I mean, it's crazy how much curiosity plays into just actually getting into something you really want to do.
Yes. Yeah. And I guess the other thing is sort of being persistent, right? And not giving up if you don't understand something at some point. You just because you have this goal you want to understand, and then you just do whatever it takes.
Yeah, I remember back in middle school, I used to ask my parents just questions nonstop, and they would get annoyed sometimes.
Yes.
It was like, it's just curiosity.
Yep.
For particle physics, what takes up most of your day in terms of particle physics as a job?
I mean, my job is sort of very, very diverse, right? Mm-hmm. Being a professor means that you have many different things to take care of, and research is only part of my daily job. That's in addition, there's of course also teaching. So I have to prepare classes, I give classes, I meet with students, I meet with graduate students who do research with me. I have many of those meetings. I have meetings with other collaborators at other institutions at other universities around the world. I have to participate in some sense the administration of the department. I'm, for example, the director of our graduate program at the physics department, so that takes part of my time as well. I help organizing the seminars that we have here at the Institute for Particle Physics at UC Santa Cruz. I help organizing conferences worldwide. I'm in committees of that. I review for journals. I review grant applications for funding agencies. So it's a lot of different things that I'm doing, and so my day-to-day work, is changes every day in some sense. So whatever is the most pressing issue is what I work on. And in terms of research itself, the time that I do have to do actual research, also that is very, very diverse. So there are very different aspects. Part of it is just learning and staying up to date what other people are doing, reading papers, reading research that other people are doing, new results that are coming out, trying to come up with new ideas, what type of research I want to do, and then coming up with a roadmap of how to do that research, and actually doing that, or involving collaborators and discuss with them, bounce back and forth ideas, trying to develop the way we want to approach that problem, doing calculations, doing numerical simulations, writing up results, sending them to journals for publication. So it's a very, very diverse set of things that I'm doing.
That sounds like a really fun day.
yes. And any given day, of course. Oh, sometimes I give interviews. I guess that's part of it as well. So
great. You had time to have me interview you.
Yes. I mean, absolutely. I mean, these are all fun things to do, and I think that's part of the thing that I really like about this job, that it is so diverse. There's no days like the one before, and you get to do new things constantly.
Yeah, that's kind of one of the things I really want to do when getting into a job is I don't want something that's just you repeatedly do the same thing over and over again. It's like when you're in this kind of field, you're constantly changing what you're doing.
Yes.
And I understand you travel too.
I travel a lot also, yes, going to conferences, to workshops. Just a few weeks ago I was in Spain for a workshop. In a couple of weeks I'll be going to a big conference called the SUSI conference, which is taking place in Oklahoma. We actually hosted the SUSI conference last year here in Santa Cruz, and I helped organizing it. So it was also a fun thing to do. Well, that is something that I really enjoy about this job, that you get to travel a lot, you get to meet many people around the world, other researchers who work on similar problems. You can exchange ideas with them. That's a very rewarding aspect of the type of research that I'm doing.
Okay, I just gotta ask this question. When you travel, do you take a vacation day? Just
Yes. Actually, I would like to do it more often than I do. Very often it's just you fly into that place where the conference is, and you participate in the conference and you fly back. Just often there's not much time to take a vacation and to take on a few days. Sometimes I definitely do. I mean, originally I'm from Germany, so I grew up close to Munich. My parents still live there, so whenever there's a conference, for example, in Munich itself, I usually just take a couple of days and visit them. So that's what I try to do. And of course, if there are conferences in sort of more exotic places, one tries to maybe a bit of sightseeing as well.
Yeah, and you mentioned you have to share ideas with other people and you collaborate with them. How does collaborating with others look like and work in terms of this?
Yeah. I mean, so if these are collaborators who are at different institutions, maybe even on a different continent, of course, one has to be sort of organized and then figure out how to collaborate effectively. It actually can work well if one knows those collaborators well. So if one is on the same page and one has a clear idea of okay, I work out this aspect of the problem, you work out that aspect, and then once a week we meet over Zoom, for example, and sort of share the results. We discuss the problems we encountered. We try to exchange and see where we are, and try to clarify aspects that we don't understand yet. So that can work very well, and I have several of these types of collaborations with people from Europe, sometimes also Asia. It can be tricky sometimes if it's a collaboration that sort of spans several continents to find the time where everybody is available for a Zoom meeting. So right now I have a collaboration with people from Cincinnati, so they are on East Coast time, and a researcher who's in Asia. So there we need to. It's tricky. So we usually do it in the evening Pacific time, which is I think early morning for the researcher in Asia, and already very late evening for the East Coast people. But that was the only time that worked for everyone. So it can be sometimes tricky if one has these type of collaborations, but one always tries to find a way to make it work.
Yeah, I mean, you have to find a way somehow.
Yep.
So when you're doing these collaborations, you eventually get to working on research papers.
Yes.
How does one go about not only figuring out what they want to research about, but also going about making a research paper?
Yes, good. I mean, the most important thing is always the question you try to answer, right? I mean, you need to come up with a good idea of what you want to research, and that requires, first of all, that you know what people already have figured out in the vicinity of that topic. What is the current state of the art in that field, and where can you sort of make a contribution, impactful contribution? What can you, which question can you answer that advances our standing in that field? And that's sort of, in some sense, almost the most difficult part of the research, coming up with the actual research idea, coming up with the question that you want to address. And once you have formulated that question in a sharp way, then typically the next steps are easy in some sense. I mean, at least you know what the question is, and you can figure out what is the way to address that question. And then you have to come up with the actual research approach, and it can be different depending on which question you're trying to answer. And assuming everything goes as planned, and it usually never goes as planned, but and there will be always some wrinkles along the way, and you have to slightly probably change maybe your question that you want to answer, or you need to change your approach in the end slightly. But assuming all that goes through, and then you arrive at you get some results in the end. While you just sort of document right along the way what you've been doing, and you describe that in a way in a paper, such that other people can reproduce what you did, and that other people can be confident that the conclusions that you reached actually make sense, that they can reproduce that.
Yeah, having to put all that data in one article, though, it just seems like, we did all of this, but now we have to simplify it into a paper.
Yes, good. Yeah, so when you write the actual paper, it's not always that it follows step by step the way you actually reach the conclusions. Often you sort of you would try to turn things around, and because in hindsight often things are much more obvious than at the beginning. So when you figured out something, then you look back at it and say, oh, actually, if I would have started thinking about it in this or that way, it would be much more obvious that this is the actual conclusion. And often then in papers you sort of try to describe things in the simplest way to arrive at the conclusion.
Yeah, we're currently working on a research paper for my Astro 9 class. It's going pretty well. It's not the easiest to put all that stuff into paper, but it's like once you get all that stuff just a little bit more simplified, you get to turn it into something that other people can use.
Yes.
And it's just it's a wonderful thing, because I know you helped publish, I want to say publish, but you're the author of, I think, if I remember correctly, more than 60 articles. If I check.
I don't know the exact number, but that sounds about right. Yes.
Yeah, and I see on the thing there's a lot of collaborators.
Yes.
In terms of actually doing the research, is there any times where opinions just clash with each other, and then you have to find a way around that?
It can happen, definitely. I mean, in the end, most of the research, I mean, there's one correct answer, right? If I do a calculation, and if I need to figure out what is the correct minus sign, where does the minus sign show up in the calculation, there is one correct answer. And though there is not much about opinions in this context, but if a collaborator of mine gets a different minus sign than I get, then we have to figure out who's wrong. Right? Only one of us can be right in that case. So that often involves then fairly lengthy discussions, because sometimes these calculations that I'm involved with are complicated, and they can take a long time to go through and to cross-check. But yeah, there can definitely be situations like that where one does arrive at different conclusions, and one needs to find out what is actually happening, what is the actual correct conclusion. And then in terms of opinions, I mean, that's more sort of in the context of judging if something is interesting. Is it interesting to pursue this research question or not? And there can be definitely different opinions. But yeah, and one just tries to come to some compromise sometimes that everybody can be represented in the paper, and all opinions sort of are taken into account when one formulates a research direction, a research question, and then tries to address it.
Yeah, do you, because I know there's research, professors do research here on campus.
Yeah.
Do you take part in any research here on campus?
Well, I mean, my research is theoretical in nature, so I'm not directly affiliated with any experiment, for example, that would be running. I mean, here on campus we don't have any big experiment running in terms of particle physics. Most of the particle physics experiments are at a scale which wouldn't allow sort of a single physics department to run something like that. I mean, the famous example would be the Large Hadron Collider.
I saw your paper on that.
Yeah, so that's sort of an enormously large experiment. It's the biggest particle collider that has ever been built. It's sort of a accelerator ring with a circumference of 27 kilometers, so it's an enormous thing. There are tens of thousands of people who are involved in that experiment. So no single physics department could manage to run such an experiment.
That would be needing a lot of people.
Yes. So this is just a worldwide effort where institutions around the world are collaborating, and many physicists here at the department, for example, are working in experiments at the LHC, my work has mainly to do with interpreting the data that is coming out from these experiments. How do the results that come out from those experiments, how do they fit into models of physics beyond the standard model? How do they fit for certain new physics models, maybe some dark matter models or something like that?
Yeah, there's when you first got into the field of particle physics, what is something you wish you knew beforehand when coming into particle physics?
Yes. Difficult question. Let me think. So I had no real idea of how research actually works in practice. I mean, this is something I learned by doing in some sense. I don't know if I would have liked to know more about that. I mean, I think it's just discovering all this stuff by myself, or in collaboration, of course, with others. But without knowing exactly what you get into, I find it interesting and more rewarding in some sense. If one then succeeds doing that. I think I didn't expect originally that what I mentioned before, that the work is so diverse that I would be ended up doing so many different things all at the same time, and I might have find that intimidating to some extent even. So I think my idea of how sort of daily work as a particle physicist would look like was much more streamlined in some sense. I do my research, I go to the office, I do some calculations, I code something on my laptop. But there's so many other things as well that are going on, which turn out to be extremely fascinating and interesting, and makes this work very exciting, which I didn't know about. But I don't know if I would have, if it would have been beneficial if I had known about that.
Yeah, I think it's interesting actually not really knowing what you're really getting into.
Yes. Yes.
Because you get to learn all of that as you go through, and that's the interesting part. If you already know what you're going to get into, it kind of feels a little bit boring, yeah. And then, that's actually, I want to think about that more too now. But okay, I want to. There's one question I wanted to ask. I think this is actually, this is a question because I posted on Instagram if anyone had any questions for you.
Okay.
One person asked me to ask you, what what skills are most important for someone to have when entering just a field in physics in general?
What skills? Well, I mean, you should have a good background in math to some extent, a good sort of analytic skills, generically speaking, and again, sort of generically speaking, part of the work, or a lot of the work that we're doing in the end, is problem solving. So the ability to understand the core of a problem, or disassemble a problem into individual pieces, address those individual pieces, and then put everything back together into a solution. So solving problems is something that I think physicists in general say is something that physicists are very good at. And having this ability to see through a problem, put it into different pieces, addressing them one by one, being persistent about it, and actually solving those problems. I think that's what's one of the characteristics of a physicist.
Yeah, one thing, there's a quote it's from Einstein. It's imagination is more important than knowledge.
Yes, I think I would agree with that. Definitely.
Yeah, I agree with that completely.
Yeah. Of course, knowledge itself is also important, right? I guess you need to, as I mentioned before, if you want to come up with an interesting research question, you need to know what are the questions that people already have answered.
Yeah.
Right? You don't just do things that is already known and you do it again. So you have to know certain things. You need to know where the status of the field is at the moment. But then the next step is indeed imagination. You have to go beyond what is known already and come up with new stuff.
Mm-hmm. There's another question that someone also asked me. It's actually in regards to research papers. Mm-hmm. It's for how do you get the funds in order, because I know sometimes when publishing papers, it requires money. How do you get the funds to actually publish papers and do research?
Yeah, so in physics, in general, I think in particle physics for sure, it's there are several journals where we don't have to pay as an author to publish. So at least in our field, you don't need funds to actually publish. It might be different in other fields. The funding in general, the research funding, comes from funding agencies. In the US, the two big ones would be NSF, National Science Foundation, and DOE, the Department of Energy. They have sort of an Office of Science which funds the research.
Really? Oh.
Yep. And so my research funding comes mainly from the Department of Energy. Okay. It's in the context of the Santa Cruz Institute for Particle Physics, SCIP, the big research organization that we have here on campus. And the entirety of SCIP, or the large parts of SCIP, are funded from grants from the Department of Energy. And part of that is funding my research. That means, for example, part of my salary during the summer gets paid from that grant. The students that I'm advising, part of their summer salary comes from that grant. When I'm traveling, that expensive come from the grant, etc.
Oh, and you actually teach classes here at Santa Cruz.
Yes.
What classes do you actually teach?
Oh, I teach a bunch of different things. So I've probably taught more than 10 different classes so far. At the moment, I'm teaching a general relativity class.
Oh,
which is very interesting. Which it's not directly related to the research that I'm doing, but general relativity is a fascinating topic. So I really enjoy teaching that. I learn a lot by myself when I teach that. That's one aspect of teaching that I in fact do like a lot. That I get to learn new things. I think whenever you have to teach something, you really have to understand it well. So it means you also have to learn it very well. And this is an aspect that I do enjoy. I teach several of the graduate level courses. So I taught, for example, electromagnetism. I will teach that again, I think, in the fall. I taught various classes, various electives, graduate electives, quantum field theory, particle physics classes for graduate students. I also taught a while ago quantum mechanics 2, the upper division undergraduate class. I think it's 139B. And I also taught the intro physics 5D, for example, a few years ago.
Oh, okay.
So across the board, I teach many different classes.
You teach 5D. Are you going to teach the 5D again?
Maybe at some point, yes. I think not this fall. This fall I will be doing the graduate E&M, but yeah, maybe in the future. So we get to know our teaching assignments. I forget exactly when we get to know this. Usually once a year.
Oh, you get notified of teaching. Oh, okay.
Yeah.
I didn't know that.
Yeah, the way it works is you can give preferences. These are my top 3 classes I would like to teach. And then they try to accommodate that. But of course, it's a complicated puzzle. Many different classes that need instructors. And yeah, so it's a puzzle that they need to put together. So I usually get classes that I do like to teach, and I can put in those preferences. And yeah, but there's every year, so it gets renewed.
Oh, yeah, that's interesting. I actually wonder how that all works. But move on from that. What should students expect to learn about here at Santa Cruz when they're trying to study particle physics?
Well, so at the undergraduate level, it's if you want to go into particle physics, it's important that you have a good foundation of physics in general. And I think that's true not only for particle physics but for any subfield of physics that you're interested in. That you need to sort of get the basics first. That means classical mechanics, electromagnetism, quantum mechanics, a bit of statistical mechanics is also often useful. So these core classes is something that one just needs as a foundation. And then on top of that, if you're mainly interested in particle physics, I think we do have an undergraduate class on particle physics, which I think is taught every year. It sort of gives you just an introduction of what are the some of the aspects of particle physics. What is the standard model? I think will be covered. Maybe also a bit of dark matter will show up in this class. Not yet at a very quantitative level, but at least at a qualitative level, it gives you an overview of what particle physics is about. What are the things we know? What are the things we don't know yet about particle physics? And then if you kind of look further at the graduate level, then you would go into sort of more specialized classes that are relevant for particle physics. One thing I mentioned that a series that I'm teaching is the quantum field theory classes. Quantum field theory is the language in some sense that we use to talk about particle physics at the quantitative level. It's a combination of quantum mechanics with special relativity. So once you combine quantum mechanics with special relativity in a consistent way, you end up with quantum field theory.
I heard quantum mechanics is really confusing.
Quantum mechanics can be confusing. That is true. Yes, I mean quantum mechanics is always relevant whenever you talk about very small things, very microscopic things. Then quantum mechanical effects become relevant, and that's particularly the case for particle physics. Right? Particles, fundamental particles, are the smallest things that we know of, and the other things that they do is because they're very small, they're very light. If you accelerate them, for example, they reach very high energies. That means they move often very fast, with speeds very close to the speed of light. That means also relativistic effects become important. So you need both quantum mechanics and special relativity to talk about particle physics.
Oh yeah, that actually brings me to one of my next questions, because when getting into a class because coming in the physics series, I didn't have any background in physics at all, so it was a huge course load for me in general.
Yes.
Do you have any advice on how people can help balance heavy course load?
Yes, that's a tough question. I mean, as I mentioned, there are many aspects that are important for a physicist, and because we, over the decades and centuries, I guess, we have accumulated an enormous amount of knowledge about how physics works, and that's something that one needs to deal with in some sense, right? I mean, you need to get up to speed and to the point where you can actually do something new, some research that goes beyond of what we know already. But because we do already know so many things, it takes a while to actually get to that point. And yeah, this might look intimidating, especially at the beginning as an undergraduate, because there's so many things that you're supposed to learn. But there's no real way around that. I think you just have to get through that. I mean, you have to get all the basics first, and then slowly start specializing into a certain area, and then it just maybe at some point if you go to graduate school, you reach a point where you then, at the end of your graduate career, you start being able to formulate your own research questions. But it takes until that point, in some sense, until you're really at a level where you're sort of an independent researcher in particle physics, where you can ask your own questions and contribute to expanding our knowledge of physics at the fundamental level.
Yeah, for chemical questions, what are actually some really big unanswered questions right now in particle physics?
Good, yes. I think one thing we already mentioned earlier, that's the issue about dark matter, that we are very, very convinced that dark matter exists, but we don't know what it is. We know very little about it. As I said, it's plausible that it's some particle. If it's a particle, we know that it can't be electrically charged, for example. Otherwise, we would have been able to detect it already. Yeah. But apart from that, there are many, many options of what dark matter can be. It could be that it's not a single particle. It could be that there are many dark matter particles out there, many different ones, and that they all behave differently. And sort of a big part of research in particle physics is about dark matter, for example, figuring out what it is, how one could detect it in a laboratory, in an experiment. Other questions are about the why is there matter and no antimatter in some sense? Or I mean, if you think about what happened after the Big Bang, sort of the naive thing would be to assume that at these times you produce the same amount of matter and antimatter, and then if this matter and antimatter again combine, they should annihilate away, and you're left with nothing. But we see a lot of stuff around us, so there is matter around. So where did that matter come from? So apparently after the Big Bang there had to be a small imbalance between the matter and the antimatter, so that everything disappeared, but part of it was left over. That's known as the baryon asymmetry of the universe, and there are various ways trying to understand why that is the case, or where this asymmetry between matter and antimatter could come from. There are other questions like the question of why gravity is so weak compared to all other forces. In general, it's very difficult to incorporate gravity in the context of quantum mechanics or in the context of particle physics. Usually we don't need to do that for actual experiments that we're running. The effect of gravity is almost always completely negligible because gravity is so weak. Right? If I can take this pen and I can easily lift it up, even though it's the entire mass of the Earth is pulling it down. But I can easily pull up this pen. The force that the entire Earth is exerting on that pen is extremely tiny, actually. So the question is, why is that the case? There's no reason in principle why gravity should be so weak. In fact, the equations that we use to describe the behavior of particles under the influence of gravity, what they want to do is they want to they want to make all the other forces of the same, roughly of the same strength as gravity in some sense. So particularly the weak the so-called electroweak force, the one that is responsible for radioactivity, that one is much stronger than gravity. But our equations want those two forces to be roughly of the same size. But they are not. They are vastly different, many orders of magnitude different, and there are attempts to explain why that is the case. For example, again with physics that goes beyond the standard one.
Yeah, I noticed particle physics has a lot of theory in it. How does theory actually come to play when it comes to like experiments?
Yes, I mean there are. It goes both ways. On the one hand, you can sort of come up with theories that try to address maybe some of the problems that we just mentioned. You write down equations that try to solve those problems. And then you can ask what are the predictions that these theories are making, and then you can sort of tell your experimentalist friends, oh, you should check this because my theory is predicting that something interesting should happen when you look for that. So that's one way. So the theories are motivating to do certain experiments or certain experimental analysis. And then the other way around, when experiments are running and taking data, then you want to understand what is coming out from these experiments, and you want to interpret the data in the context maybe of your models that you've written down. Is the data compatible with the model that I've worked on, or not? Maybe can I use the data to conclude that this model or this theory that I'm working on is actually excluded because it actually contradicts what the experiment is finding.
Yeah, when you're trying to actually, so let's say there's like for dark matter in general, how do you go about actually making an equation that help figure that out?
Good, yes. So the one thing, if I write down a theory for dark matter, I can for example compute the probability that a dark matter particle comes in and scatters in a chunk of material. Experiments that look for dark matter often work with things like xenon, for example. They have they're big tanks of xenon, and they look for dark matter scattering on xenon, and this is something that in a theory I can predict. So how often would the dark matter scatter, how much energy would it deposit in that scattering process, and then I can compare that with the actual data that is being taken. And because so far none of these experiments has detected dark matter, I can sort of exclude certain models of dark matter because they would have predicted that the experiment should have already seen these scattering events from dark matter.
Yeah, when it comes to, because you also have to figure out, if this research paper explains this, what happens when there's something that contradicts a research paper?
Right. So if there are experiments that contradict a certain prediction of a model, then the model is ruled out, and then we know that model can't be true, right? So that we can get rid of that model and need to move on to something else. That's actually in the end, it's always the experiment that decides if a model or a theory works or not. Right? If the experiment contradicts the theory is dead, and you should come up with a new one. And that's often very challenging because, as I mentioned, the standard model of particle physics works extremely well. So all the measurements, all the experiments that are being done, they are compatible with the standard model. All the predictions of the standard model are verified by those experiments. So whenever you add something on top of the standard model, some new physics, you have to make sure that none of these experimental results that we have, that the model doesn't predict any violations of these experimental results. So you need to make sure that the model, the theory, only does what you want to do, but doesn't screw up things that we already have established.
Yeah, and I have actually just one more question for you from someone else. What are some actually like recent discoveries or developments in particle physics that you've been actually interested in?
Okay, good question. I mean, the big discovery, which already goes back now almost more than a decade, is the discovery of the Higgs boson. That's something that has been extremely exciting, which happened during the time that I was a postdoc, for example. So after I got my PhD in 2010, the discovery of the Higgs boson was in 2012. And that sort of was the one last missing piece of the standard model of particle physics that hadn't been discovered yet. So it's the last particle to be discovered. And this was really, really exciting that we had this prediction that this Higgs boson should exist, and then the LHC, the Large Hadron Collider, actually found it. And now part of the research that's still going on at the LHC is just trying to measure the properties of this Higgs boson as precisely as possible. How does it get produced? How does it decay? What are all its properties? And that's that will continue to go on for a long time still, just trying to characterize the Higgs as precisely as possible. Beyond that, my research, part of my research is related to so-called decays of B mesons. That's another type of particle that gets produced at the LHC, and one can measure it very, very precisely. And yeah, so sort of the most recently, my research has been just analyzing or interpreting data that's coming out from measurements at the LHC of those B mesons, and try to understand if the measurements are actually compatible with standard model predictions or not. If there's anything that points to physics beyond the standard model.
Yeah, that's for because you've got to, when you're doing these experiments, you gotta know your stuff. Because for me personally, every once in a while I forget this and I forget that. How do you go about memorizing all of this stuff?
Oh well, it comes with time, I guess. So I often need to look up things because I forget them. But at some point, if there's this one thing that you always forget and you have to always look it up, at some point you decide, okay, it's too much work to just look that up all the time. Now I need to really memorize it. So certain things one just memorizes it because it gets too annoying to always look it up again over and over. But yeah, there are many things that I forget, and indeed, I guess one way of phrasing it is knowing things means knowing where to look it up, I guess. So, you just need to know where to find the information ultimately.
Well, that was my last question. Well, thank you so much for meeting with me today, Professor. Before we actually end off, do you have any advice for the people watching that want to get into particle physics?
My advice would be, if you're really interested in particle physics and want to do particle physics, be persistent, right? I mean, don't get discouraged if there's something that doesn't work the way you think it should immediately, or if there's something that you don't understand, or just be persistent. Don't give up. And if it's really thing that you want to do, if you're curious about particle physics, you want to understand how nature works at the fundamental level, just do it, and be persistent.
Yeah. Well, thank you so much.
Sure.
That was really great. Well, thank you guys for watching my podcast. Remember, I'm trying to do this once a month, and hope you guys look forward to the next one. And goodbye.